Are you recording?
I am recording. If you would,
Okay. So, hi, I'm Bill Waller, and it's the monthly GAAC meeting for July 10th, 2020. I'll be talking about galaxy blowhards, or how I learned to love galactic theatrics. This talk will also serve as Earth and Space Report number 4. This is a series of reports that I do monthly on all topics having to do with Earth and space. These reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our human relations with the terrestrial environment, and who wonder about the greater cosmos, our place in space and moment in time. So with that, let's get started with galaxies. Oops, there we go. Oh, I'm having trouble.
page down.
I'm having trouble making it advance.
Okay. Did you hit page down or the down arrow?
Yeah, the down arrow.
Space bar?
Maybe I should escape again. Oh, I might be frozen. Is that possible? No? Okay, I got it now. There we go. Okay. So, so galaxies, 100 years ago, nobody knew about galaxies. But that changed around 1918 with Harlow Shapley, who was the director of Harvard College Observatory for a while and then moved to California to continue his work. But around 1918, he worked on finding the distances to globular clusters. These are clusters of stars which look globular. And over here, you can see the globular clusters. They're encircled right here. And what he found was that the globular clusters were themselves clustered not all around the sun, but in a single direction towards the constellation of Sagittarius. And that's also the direction where the Milky Way is brightest. You can see the star clouds of Sagittarius here, the star clouds which make up the brightest part of the Milky Way. And he used RR Lyra variable stars to allow him to figure out the distances to these globular clusters. And yes, indeed, they all were clustered far from the sun at a point around 50,000 light years away from us. Okay, so he made the leap, the logical leap, that if the globular clusters are themselves displaced from where we are, then probably the this thing he called the metagalaxy was located, its center was located not where we are, but in Sagittarius 50,000 light years away. His metagalaxy concept lasted for a little while, oops, wrong way, until Edwin Hubble came along in around 1923, and he was taking many, many photographic plates of the great nebula in Andromeda. And he discovered that there was one object in the great nebula which was varying, just like one over here. He saw one varying here. But this one, he thought at first it was a nova, but then he noticed that it dimmed, but then it brightened again. And then he got enough plates to realize that it was dimming and brightening with a regular period. Hence, it was a variable star. That's what he concluded. And it was a Cepheid variable stars, which he knew something about elsewhere in our own galaxy. And so he realized that at its apparent brightness, this object and the host nebula must be very, very far away, 100 times farther away than anything else that was then known at the time. And so at that point, our universe blew up in our face, and we were contending with island universes known as autonomous galaxies. And since then, we have come to realize that the universe is just riddled with galaxies. I say countless here. That's not really true. You can estimation for the number of galaxies that are contained in this Hubble ultra deep field. And I should let you know that the size of this field of view is the equivalent to the eye of Franklin Delano Roosevelt on a dime, placed at arm's length. That's the piece of sky that you're looking at here. And all of these objects here are galaxies, okay? And so you can actually go through the exercise. Space Place provides this exercise. You can count the number of galaxies in a subset of this image, and then they give you the multiplicative factor to compensate for the rest of the sky, and you come up with invariably around 50 billion to 100 billion galaxies that can be seen in this one image, extrapolated to the entire sky. So in truth, galaxies are the largest self-gravitating systems of luminous matter in the cosmos. This is where it all happens as far as evolution leading to moist planets like Earth and life on these moist planets. It all happens in galaxies. Okay, so there was a lot of great galactic research that was presented in early June, June 1 to 3, during the 236th meeting of the American Astronomical Society. And this meeting was supposed to be held in Wisconsin, but it was held virtually for the first time ever. And you can see here that there is a .com. This is how I was able to get into the gain access to the meeting. And so they had a private company provide the interface. And let me show you the interface. They had kind of like this animated interface of what it would be like if you were actually at the meeting. I'd have to say that they got the diversity pretty good in terms of all the people who were milling around. This was all in motion. There are people of color, people of different genders, but I'd have to say that as far as age, they didn't get the diversity right. There aren't any old farts like myself in the meeting right there, as I can see. Anyways, I was able to get into this meeting using my press credentials as co-editor with Mike Deneen of the Galactic Inquirer, which is a free online journal for anything that has an astronomical theme to it. Okay, so once you get into here and you sign in, I went mostly for the oral sessions. There was also poster sessions, and I have to say that there was a wide variety of topics that were discussed, from finding planets around other stars to the cosmic web and the acceleration of the Galaxian universe and dark matter and dark energy. I mean, as usual, it covered the whole range of topics in astronomy. But I'm going to focus on galaxies, and in particular, the galaxies which have big winds, all right? And I'll begin with a talk by Elizabeth Mills about gaseous anomalies. Anomaly means strangenesses, something unique about the gas near the Milky Way's center. And that will set the stage for what's going on in the Milky Way's center and what's not going on. What they have discovered is this thing called the Fermi bubble, the Milky Way's Fermi bubble right here. And there's a whole stable of folks who talked about that. And so I'll discuss that. That's about as expressive as our Milky Way's center gets. But there are other galaxies which are far more expressive. And those are summarized by Christy Tremonti in her talk about intense winds blowing from other galaxies. All right. So we begin with Elizabeth Mills from University of Kansas, or Kansas University. Journey to the Center of the Galaxy, Following the Gas to Understand Past and Future Activity in Galaxy Nuclei. And I'd have to say her talk was fabulous. It was very animated. She did a great job, and she stood throughout her talk, just like in a real talk. I was impressed by that. So the first thing to note is that we are not 50,000 light years away from the center of the galaxy, as Shapley said. We are about half that. Our distance measurements have gotten improved, and so the uncertainty is more like between 25,000 and 28,000 light years. That's what we think the distance is. And along the way, you can see in this artist's simulation, if you will, artist rendering, there's a whole lot of dust that's in the way. Dust clouds are in the way. And so we have trouble seeing the center of the Milky Way galaxy at visible wavelengths. And this can also be seen in an actual mosaic of the visible Milky Way. And to give you some idea of where we are or what you're seeing, here is the North America Nebula in Cygnus. And so that's something many of you would know. That's at around a galactic longitude of around 110 degrees. And then here is the Carina Nebula on the other side, in the constellation of Carina, which is seen in the southern hemisphere. Here is the Coalsack and the Crux constellation, which is in the Australian flag and the New Zealand flag. And then here is our nearest star other than the sun to us. This is Alpha Centauri and Beta Centauri, okay? So she focused in on this area, and you can see that it's highly obscured by foreground clouds of obscuring dust. And this piece of territory is around 6,000 light years, but then she focused in to about a tenth of that, to about a 600 light year piece of territory. And here it is. And this is known as the central molecular zone. And what we have here is a multi-wavelength view of what can be seen at infrared, radio, and millimeter wavelengths. And each of those wavelengths pick up different aspects of what's going on there. And in the infrared, it's sensitive to the emission from hot dust. The dust has been emitted by stars. The hot dust has been irradiated by stars and caused to glow. So that's the green emission around here. That's basically not scattered light, but actual re-radiation by the star-warmed dust. Then there's the radio in purple, and you can see that it has some very interesting features associated with hot gas, and a plasma is even hotter. That's when the electrons get ripped off of the atoms, and they're twirling around lines of magnetic fields. And so this structure probably has been magnetically structured, magnetically organized. And then, of course, in the radio, the true center of our Milky Way galaxy shines very, very brightly. This is known as Sagittarius A. Then at millimeter wavelengths, what you're seeing is very cold dust, just glowing at a very low temperature. And then there are molecules, different kinds of molecules that are glowing at millimeter wavelengths. So all of these require different kinds of telescopes, and this has been put together after probably a lot of observing and mosaicing. Okay. Here is the same field of view in the radio with a very recent mapping by Meerkat. That is an array of radio telescopes that are in South Africa. And you can see a whole bunch of really amazing features. They're all associated with recent massive star birth and star death. So what we're seeing is what happened a short time ago, recent past. You have these round things, those are supernova remnants. But those are the results of massive stars having exploded. This one, and this one. Those are supernova remnants. Then there are these bright objects, and those are bright starburst regions or emission nebulae where stars have yet to blow up, but they are zorching their surroundings, the surroundings which gave birth to them, okay? Their ultraviolet light is fluorescing the nebulae, ionizing and fluorescing those nebulae to glow. And in the radio, you're again seeing very hot gas, tens of thousands of degrees, and the electrons are screaming their annoyance. Again, the center of our galaxy is very, very bright, Sagittarius A. And then they're here, you can see in the radio, these, the arches, the so-called arches that are associated with Sagittarius A, but more to positive longitudes. Then you probably have noticed these things, these threads or filaments, these very, very narrow objects which remain a mystery, okay? And I'll get into that a little bit later. So already you can see that the galactic center, the central molecular zone, is odd, it's unique. Okay, then we have what's happening today. Stars have come into being, stars are glowing, stars are irradiating the dust, and the dust in turn is glowing. And based on the emission by the dust, along with the emission by the stars themselves in the infrared, they can determine how many stars there are. And they estimate that there's about 1 billion suns worth of stars there. And that corresponds to about 2% of all the stars in the Milky Way galaxy. So it's significant in this tiny little zone of 600 light years size. So that's the stars that are. And then I think the specialty of Dr. Mills is the stars that will be, and that's contained in the molecular clouds, the molecular gas that's emitting at millimeter wavelengths. And the dominant molecule is molecular hydrogen, H2, but it does not emit well, so we have proxy molecules that emit strongly at millimeter wavelengths. And so you can trace out the gas that is in these clouds, and this is where stars are about to be formed. It's the stars that will be. These are the nursery wards of the stars. And they've found some very fascinating properties of these clouds. But first I'll get to the idea that she was talking about the journey towards the galactic center. And she was wondering whether that journey is more interesting than the destination. But I'd have to say that she didn't talk that much about the journey, except to just note that probably there is a funneling of the gas from the disk of the galaxy towards the center along the bar. And the bar is basically a stellar bar. It's an instability in our swirling disk that stays put at least on the order of hundreds of millions of years. And the gas probably funnels in this way. And what her group has determined, whoops, sorry, not yet. So we'll talk about the destination first, okay? The central molecular zone, you have a 300 light year extent here, but she homes in on this 20 light year region centered on the galactic center, or almost centered on the galactic center, and blows it up. Here's 20 light years. And the first object that you can see is called Sagittarius A East. They think it's a kind of a hybrid between an emission nebula from a rampant star formation and a supernova remnant. They thought that it was associated with Sagittarius A West, which is this thing, but now they think that it's probably in front of us, in front of Sagittarius A West as seen by us. And in this figure, she did this all, one at a time, but I just did the last slide, so just follow my mouse. You go from 20 light year extent to a 10 light year extent, zooming in, and you can see what is called here a circumnuclear disk. It also has kind of a ring-like quality too. So this is the stars that will be the gas, molecular gas is piled up into this ring, and inside of this ring is what they call a mini spiral, and that's shown here at a high magnification from 10 light years to 1.5 light years, and here's a portion of the mini spiral. The gas is thought to be coming inwards. This is the first time you can actually see Sagittarius A star, the actual center of the galaxy, which traces the supermassive black hole. So you go from 1.5 light years to 0.45 light years. We're now not in the radio regime, we're in an infrared regime where you can actually see the stars. And there seems to be quite a few stars, many of which are massive and hence short-lived stars. That means that they were formed recently. Moving in closer to Sagittarius A from 0.45 light years to 0.1 light years, so we're decreasing the size by a factor of 5 or so, and you can actually see the stars in orbit. This is seen in the near infrared using the Keck telescope on top of Mauna Kea in Hawaii, and they have been tracking these stars as they've been going around a common center. They've been tracking this for more than a decade, and these stars are zipping around with orbital periods of about a decade. Compare that to our orbital period around the center of the galaxy. The sun and solar system goes around once every 220 million years, okay? These stars go around in around a decade. And the stars closest to the galactic center, like S02 here, they give you the best estimate for the mass of what's inside. By using the orbital period and the size of the orbit, they can determine that whatever's inside, and they think it's a supermassive black hole, has a mass of around 4 million suns, 4 million solar masses. And it's all contained within a region smaller than the solar system. The only explanation that most astrophysicists can come up with is that it must be a supermassive black hole in there. They've been trying to observe it with the Event Horizon Telescope. This goes from 0.1 light year to basically, I think a millionth of a light year. This is the array of telescopes which are spread out over the entire Earth, the Event Horizon Telescope. And this is not an actual image. They have had tremendous success getting the image of the supermassive black hole in another galaxy, M87, a supergiant elliptical galaxy, but they've had trouble with this one so far, and that's because things are moving as they build up their observations, and so they're having trouble putting everything back together. But so this simulation shows what they think would be seen. The black area is a shadow of the event horizon, and so I think the event horizon itself is a little bit smaller, but this is the shadow cast by the event horizon, and all this emission is from material surrounding the event horizon, and it has been gravitationally lensed into a complex of rings. Okay, so we've made the circuit of this very interesting image going down from 300 light years to about a millionth of a light year. Okay. What they have found back at the 300 light year scale is that the molecular clouds are unusually dense. They have a number of hydrogen molecules per cubic centimeter is about 1,000 to 1,000,000. And whereas the molecular clouds in our neck of the woods would be on the order of about 100 particles per centimeter cubed. So the clouds are denser. Then they're also warmer. They have temperatures of 50 to 300 kelvins. 300 Kelvin is what you're feeling right now, room temperature. So they're pretty warm compared to the molecular clouds in our neck of the woods, like the Taurus molecular cloud and the Orion molecular cloud. Ours are just a few kelvins, a few degrees above absolute zero. And then lastly, they're more turbulent. They have, as you can see here, this is the turbulent velocity, symbol for turbulent velocity, and it's around 2 to 10 kilometers per second. And by comparison, the turbulent velocities in the molecular clouds in our area is around 1/10 of that. So it would be around 0.2 to 1 kilometers per second. And if you home in closer to the circumnuclear disk at 10 light years, the turbulence goes up. So she made her point that we're dealing with special circumstances near the center of the Milky Way galaxy, which could lead to some very interesting theatrics down the line. Right now, there isn't that much starburst activity from the center of our galaxy, and the black hole itself is not very busy. And so she showed that by comparing the Milky Way with other galaxies, nearby galaxies in the local universe. And by comparison, our Milky Way has, in its center, has comparatively little star formation or black hole activity. If you go out, let's see, about 3 times 3, about 10 million light years away, NGC 253, you'll see lots of star formation. It's a starburst galaxy, and the starburst is in the center of that galaxy, but you won't see black hole activity. NGC 4945, which I think is a favorite of Mario Motta, it's an edge-on galaxy, beautiful edge-on galaxy. You see lots of star formation and black hole activity. And then there's the galaxy Circinus, and by comparison, it has very little star formation, but lots of black hole activity with jets and such. And so we see kind of an interesting variety. I think the conclusion is that it depends on when you're looking. The Milky Way could have been active in the past, and perhaps it could be active in the future. Circinus probably had a lot of star formation in the deep past, and we're currently seeing it with a lot of black hole activity. It depends on where you are and when you are. Okay. All right. So she concluded that with this deep dive into the center of our galaxy and comparison, thanks to the ALMA radio telescope in the southern hemisphere in Chile, we're finally beginning to place our galactic center in context with other nearby galaxies. And that with the Milky Way, we can really isolate the physics that governs the life and growth of galaxy nuclei in a way that is more difficult to do with the other galaxies. Okay, so that was a great talk. And so now we'll move on to what our Milky Way has been doing in terms of expressing itself. We've found that these unusual gas properties have corresponding expressions beyond the plane of the Milky Way, and it's in the form of what is now called, well, it was called a gamma ray and radio emitting Fermi haze, but now it's recognized as the Fermi bubble. And a whole bunch of folks talked about that, and I'll get right to it. So here is the history recounted by Doug Finkbeiner. They knew that there was something strange going on in the galactic center looking in the radio. And it's synchrotron emission, so that's electrons moving at relativistic speeds in the presence of magnetic fields. And there seemed to be some sort of interesting haze towards the center of the galaxy. And even after taking out identifiable objects, there still seemed to be a remnant haze. So too, with the Fermi Gamma Ray Telescope that was deployed by the space shuttle, there seemed to be something going on near the center of the galaxy. And after eliminating other possible sources, there still remained what seemed to be an interesting haze, what they called the Fermi haze. okay? And Doug Finkbeiner got very interested in this because he was looking for dark matter, evidence of dark matter. And so perhaps this gamma ray emission, the so-called Fermi haze, could be the result of dark matter annihilating, okay? So he was very interested for that reason, but then he kept with it even after that was ruled out. Here is some better processing. They used a template which modeled the disk of the galaxy, the thin disk of the galaxy, the thicker disk of the galaxy, or the bulge of the galaxy, and some semblance of these bubbles. And the result, this is the residual, and you can see that there's something strange going on above and below the plane of the galaxy. Then they did a little more work with templates. I didn't quite understand that stuff, but they came to see really what looks like a bubble. And I think it extends, I don't know, 50 parsecs, so maybe 150 light years below the galactic plane, not really sure. So they thought they really had something. And this was just with the initial data release from the Fermi Gamma Ray Telescope. All right. In the meantime, another array of telescopes on the ground, radio telescopes on the ground called Meerkat, was doing wonderful things. This is an array in South Africa. And what they found was another bubble. Here's the galactic center, but there's this other bubble that they discovered along with those filaments, okay? And Farhad Yousafzadeh, in his talk, was championing the idea that it's cosmic rays which are powering this bubble. Okay. And here is another mapping of the bubble. You can see it in black on white or gray on white. And it's offset from the true galactic center. So it's not clear whether it's being powered by stuff in the galactic center or maybe some mix of supernovae. He did note that the filaments seem to trace the outflow itself, the walls of the outflow, etc. And then he notes that there's this plasma emitting X-rays. He just showed the location. But these energies, which they estimate for the bubble, okay, that is 140 by 430 parsecs. So the bubble's bigger than, I believe, the Fermi bubble, that bubble. Anyway, this could be this energy could be produced by several supernova remnants, supernova explosions, and oops. So too, I'll move on to, here we go. The X-rays. This is an X-ray mapping. I can't remember, I think it's a Japanese satellite that mapped it. Here's the center of the galaxy, Sagittarius A, and they see these lobes of X-ray emission, diffuse X-ray emission, suggestive of a very hot gas and very high energies associated with it, consistent with at least several supernova explosions having blown in this one confined space. And here is a kind of a cleaned up version of the Fermi bubbles seen in gamma rays, the highest energies ever. And so too, the energies are consistent with a bunch of supernova blasts. But it's also possible that there's something being produced by the supermassive black hole as well. He presented a model showing the disk of the galaxy with its magnetic field, and then the cosmic rays in his model heat the gas and push it out of the plane in a wind, and that wind drags the magnetic field with it, and that produces the shape of the bubble that was seen. So fascinating stuff. He also had a model for those filaments, those threads seen at radio wavelengths. Some of them are associated with compact radio sources, which could be outgassing stars, very young stars that are outgassing quite a bit. And so he thought that maybe what we're seeing is like a comet effect. You have the wind blowing on the outgassing star, and it's producing, and the star is moving in one direction, and the net addition of all these vectors would produce a cometary tail in this direction. But in another talk by somebody else, they noted that at least some of these filaments also show X-ray emission. I think that would be very hard to explain using this model. So stay tuned on this. They remain a mystery. Okay, Rongman-Bordeloi talked about the anatomy of the Fermi bubble, and as seen from the vantage of the sun and solar system, we see the X-ray emission along the walls of the bubble, and the gamma ray emission and the radio emission inside the bubble. And this is where the galactic wind is blowing. And the energy source, he said it could be something from the active galactic nucleus, the supermassive black hole, or it could be nuclear star formation near the galactic center, which was perhaps more active just a few million years ago. Okay. But what he and his group have done is to actually kind of take cross sections of the bubble by looking at distant quasars. These distant quasars are called active galactic nuclei, AGNs. They're like spotlights that shine through the bubble, and then the Hubble Space Telescope takes a spectrum of the light that has passed through the bubble, okay? And based on that, they've been able to figure out what's in the bubble and how the bubble is moving, which is pretty awesome. Here are the sight lines. These are the active galactic nuclei in green. But then they also looked at stars bright enough to provide the searchlight capability. Let's see, the stars nearby are in orange. They're in front of the bubble. We know that. We know the distance to those stars. And then the red stars are behind the putative bubble. So in this way, they were going to be able to constrain what's in the bubble by looking at what's behind and what's in front. And he talked about one particular sight line in particular towards the quasar QSO PDS 456. And this is what he saw. He saw silicon-3, so that's twice ionized silicon. So it's hot gas, which is absorbing the quasar's light. And this would be the nominal wavelength, you know, essentially zero wavelength of absorption. But he also saw some absorption that was blue shifted and some absorptions that were red shifted that could be associated with this same spectral line. And so he interprets the blue shifted absorption according to the Doppler effect, that the light was shifted to the blue, or the absorption was shifted towards the blue, because the gas that was absorbing is coming towards us. And so too, this red shifted absorption is from gas that is going away from us. And from that, he used this model, a biconical outflow model, whereby this part of the conical outflow is coming towards the sun. And so that was producing the blue shifted absorption, whereas this part of the absorption, this part of the outflow is going away from the sun, and that produces the red shifted absorption. And he focused on that one particular quasar, but was probably the best data, but they've done it across over all those other sight lines. And so I think they're going to have some great data, basically doing kind of what you do with those X-ray tomography of the body, you know, reconstructing the bubble and its motions. Elaine Fraser also did some similar work having to do with the nuclear activity of the galactic halo. She did spectroscopy as well. It was kind of neat. And she made use of the Large Magellanic Cloud and the Small Magellanic Cloud, and its associated Magellanic Stream of gas. It also has a leading arm of gas, and they looked at the gas here with a spectroscope. I think it was the Hubble Space Telescope, and they looked at the excitation of the gas. Having the gas has been blasted by a flash of energy from the center of the galaxy, probably associated with the Fermi bubble. There was a flaring here, and it excited the gas in a certain way, which is not seen in the gas here. This gas has recently passed through the extended disk of the Milky Way, and so it has been collisionally ionized, and you see the corresponding excitations in the gas. This one has been photoionized and photo-excited, and so they make a difference between what they see here with what they see there. And it provides evidence for prior flaring of the galactic center. So it leads to this idea that our Milky Way galaxy was more active in the past. And so she concludes that the collisional excitation for the leading arm from passing through the Milky Way disk, the kinematics of the stream show that it is single phase, whereas in the stream itself, yes, kinematics of the stream show that it's single phase, and that's due to photoionization from a galactic flare. So she finds evidence for the Milky Way center having flared recently. Okay, but wait, there's more on the Fermi bubble. Dinesh Krishnarao, who represents the Wisconsin WAM, it's called WAM, Wisconsin H alpha mapper. They have found optical line emission. I've been talking about spectral line absorption, but he's actually found the bubble in emission in the optical, which is pretty impressive. And so he uses the same distant quasar. They've looked at several quasars. In other words, they looked in the same sight lines as the absorption spectrum folk. Here's that prior absorption spectrum with the zero velocity absorption, say, of silicon-3. There's the blue shifted component from the near part of the bubble. And here's the red shifted component from the far side of the bubble, the expanding bubble. But they looked in the same direction, and what they found was, yes, there's lots of emission of hydrogen alpha emission. That's that red color emission. Yes, there's a lot of that at the nominal zero velocity, just the nominal wavelength from foreground material. But then there's also at wavelengths, shorter wavelengths, corresponding to Doppler shifted velocities of around 200 kilometers per second coming towards us, they see another component of H alpha emission there. So that is a discovery of the expanding bubble, a bubble of hot ionized hydrogen gas expanding away. So that's all I have to show on the Milky Way galaxy. And to wrap things up, Christy Tremonti talked about galaxies in general, Gone with the Galactic Wind, how feedback shapes galaxy evolution. And she started off with a beautiful image of basically a star-bursting cluster of a star-bursting region, which has a very young, dense cluster of stars, some of them very massive and bright. This is in the Small Magellanic Clouds. It's called NGC 602. And you can see a whole lot of emptiness. What was there before was a whole lot of gas. So something has happened. Those stars have lit up, and their ultraviolet light has excavated this region, okay? Producing pillars, which are always pointing towards the hot stars. Here's pillars pointing towards the hot stars. So it's a lot of negative space for your art type folks. And So this is an example of feedback. It tends to be negative feedback, though it can prompt secondary star formation along the edges. But basically, these stars are returning a whole lot of energy in the form of ultraviolet light and winds. And then, of course, these stars blow up real good, and that produces supernova explosions and remnants as well. And ultimately, if you get enough of this stuff going on, you'll get a big wind. And here's a big wind. M82, which has been imaged by several members of the club and is a favorite of Elaine. This is seen at multiple wavelengths. The optical is shown in green, coded green, and that's the stars in this edge-on galaxy, this galaxy seen nearly edge-on. The X-ray is shown in blue. This is very hot gas, 10 million to 100 million degree gas, which can only be from explosions, supernova explosions. And then there's the infrared, which traces the dust which has been irradiated by the stars. And here is a model. Basically, your eye is over here. I think they left out, this is not where you're looking. The eye is over here. You're seeing it nearly edge on, and you're seeing the stuff exploding, blowing out above and below the galaxy. It's probably exceeded escape velocity, and that's something which she gets into, that this gas is no longer going to be available for star formation, and it's going to be enriching the intergalactic medium. It also, a major effect is that it slows down the star formation. So the history of star formation in the galaxy gets delayed. Without feedback, this is a galaxy seen long ago, high redshift. Without the feedback, there'd be this huge burst of star formation, and then a rapid decline of star formation. But with feedback, you get a delay and then a flatter curve. Talk about flattening the curve. Here it is. And so you can have more prolonged star formation at a relatively lower amount. For a galaxy like M81, it would be a huge burst. Of course, it has to make its central bulge, but then without the feedback, there would be this big decline, but you can, again, delay and prolong the star formation with feedback. And that's because of all that energy that gets injected into the system. It slows things down. Gravity is no longer winning against all these other energetic effects. Here's the Milky Way without the feedback, and then with the feedback. It's been nearly continuous for the past, well, for a long period of time of order. They're just talking about the first half a billion years, but maybe this could continue. And then the Small Magellanic Cloud, the same sort of thing. It's just starting to ramp up. Okay, so feedback is an important aspect to how galaxies live out their lives. It also affects the structure of the galaxies. Without the feedback, you get a big bulge. But if you have a big blast wave, that could be from the supermassive black hole, or with super bubbles from lots of star formation, you end up getting more activity in the disk and less of a bulge. So these are, of course, model simulations, but that seems to be a direction in which feedback takes us. Finally, feedback can remove matter from the galaxy entirely. This is a bigger effect for the low mass galaxies. And so they have this plot of how enriched the galaxy is with the metals that have been made in the starburst activity. And so for a low mass galaxy, you find that there's very low metallicities that it has because the metals have been blown out. Whereas with a high mass galaxy, it can entrap, entrap the gas. Maybe you can get a fountain going, but the gas won't escape. So that's one aspect, that the small galaxies will lose its metals, the metals that get made in the supernova explosions, and they will feed the circumgalactic medium. So how much of an extent is this effect? Well, there's this one galaxy. I can't remember the name of this galaxy, but it had a big outflow, a big wind, galactic wind, and this extent, I think, is what you would see in the visible. But what they saw, I think this is in the radio or in the X-rays, I forgot. But these are hundreds of kiloparsecs, so that's around 300,000 light years with the scale bar. And so this galaxy is really blowing it out. And so we're now seeing that galaxies, when they're in the on position, as far as their starburst activity, the star formation, and as far as their active galactic nuclei, when they're in the on position, they can really affect their intergalactic environment. And so, but what produces it? It depends. And if you are in a different region, it will also depend. Yes, you can have supernova explosions, but you could also just have stellar winds. Supernova explosions are a very episodic thing. It just happens, and they only last a few tens of thousands of years. They're remnants expanding, but the stellar winds can last for millions of years, and so they can have an effect. Then there's the radiation pressure on the dust grains. The photons of light carry momentum and can exert pressures on grains of dust, and that can move the grains of dust outward, and the dust can drag gas along with it. Then there's also just photoionization heating. You blast it with ultraviolet and X-rays, the gas, and what was once molecular, the molecules get torn apart into atoms, and what was once atomic, the electrons got torn off into what is now a plasma at a much higher temperature, and just hotter things have a greater pressure and they will simply expand. So that picture of NGC 602 shows that the cavitation that can result, the excavation and the cavitation that can result from that sort of photoionization heating. And then finally, this cosmic rays. That's something that can come from both the supernova explosions and supermassive black holes. So there's lots to consider and to pick apart, and to see which of these processes matters most in which settings. So I think that's it. Oh yes, here we go. She notes in this this region, this is definitely a starburst in our own galaxy. You can see pillars, resistive pillars pointing towards the cluster, a very dense cluster of stars, some of which are very massive. And it's those massive stars that produce most of the feedback. And therefore, the effects of the feedback are largest when the star formation is clustered in space and time. So you have to have large amounts of gas producing large, many stars together, the most massive of which will pop off. And also, if it's in the galactic center, it's these dense clouds of gas that will feed the supermassive black hole. Do all galaxies drive galactic winds? She overlaid this picture of NGC 891, where you can see star formation in red here and lots of dust. And she overlaid a model of what happens when one of these things pop off. You can get isolated super bubbles, but in a big galaxy like this, you get a fountain. It just comes back down. And so that's what the models show. I don't know if they have much evidence for the downward part of the cycle, but the models seem to be all pointing in this direction. Smaller galaxy, the stuff will just blow out. And again, she points to high surface densities, which means concentrated activity. And in this, I believe this is a Hubble Space Telescope image, plus X-ray in the blue. And you can see a big outflow, kind of like the Fermi bubble on steroids in this galaxy, seen edge on. When the superbubbles overlap from individual supernovae, when they begin to overlap, they can really drive a big wind. Okay. Again, trying to answer this question, do all galaxies drive galactic winds? They do find that most of the big winds are primarily found in starburst galaxies. These winds are not to be confused by jets, which are far more narrow and confined magnetically. But these big broad winds seem to be found in starburst galaxies. Here's M82. It's not its twin, but something it's probably interacted with. This should be M81, I have to say. But this is something that can be easily seen with our amateur telescopes. All right, back to M82, because it's one of the nearest nuclear starbursts. They have determined stuff, got some good physics. The galaxy is about 10 million light years away. The dynamical mass is about 10 billion solar masses. That's considerably less massive than our galaxy. But its star formation rate is considerably higher than what our star formation rate is. Ours is about 1 sun's worth of mass per year, and here we have 7 to 10. And this is a number of star formation rate surface density. That just tells you how concentrated it is. You know, how much star formation do you get per square kiloparsec? And so it all comes down to the intensity or the surface density of star formation. Okay. Here is another rendering showing the X-rays from the Chandra X-ray satellite. And in the inner part, you have hard X-rays corresponding to very hot gas, whereas in the outer parts, you have relatively cooler gas at around 10 million degrees. And that's where the outflow is meeting ambient material. It's shocking ambient material. And so that's another takeaway, is there's lots of shock activity going on. And that was also an explanation for what's going on in the center of our galaxy, why you have such high turbulence and warm temperatures. Shocks are an important physical process that occurs on multiple scales. Again, M82, they have the molecular gas. This is what's the future for M82 in terms of star formation. It's not done yet. The H1 is a big outflow. This is the neutral gas. And then in the red, this is the warm dust and molecules, the polycyclic aromatic hydrocarbons that are emanating from this galaxy. And so she concludes that galactic winds are a truly multi-phase phenomenon. And so to understand it, you have to understand the molecular phase, the neutral atomic phase, the ionized phase, and the wicked hot plasma phase, and then of course the solid dust phase. So it's a big story that one needs to weave together. Finally, she considers the other galaxies besides M82. This is about as far as you can go, even with the Hubble Space Telescope, before you lose detail. And you can see several galaxies seen edge-on with bipolar outflows. Here's NGC 253 with its bipolar outflow, and NGC 891, that was the one seen edge-on, and it has a big halo of X-ray emitting gas as well. So but after that, it's difficult to image these winds outside of the local universe with distances greater than about 600 million light years. Did I get, no, 60 million light years. That's out to the Virgo cluster. So, so what do you do if you can't image this stuff? Well, you've got a lot of questions. How do these velocities, outflow velocities, depend on the host galaxies? How much mass do the galaxies eject? You know, how big of an effect is this? How far do the winds get? And do they interact with a circumgalactic medium? And so there are some answers through spectroscopy, again with absorption lines using quasars as searchlights. And here is velocity versus the star formation rate per unit mass of the galaxy, and there doesn't seem to be much of a relationship. This is just basically a scatter diagram. But some relationship seems to occur when you look at the velocities that can be measured in terms of the star formation rate per unit area. So that's the intensity or surface density of star formation. And this kind of makes sense. I mean, if you have a more intense star bursting region, you're going to get a more rapid velocity of expulsion. And then she ends with this, probably the biggest winner of how influential these galactic blowhards can be. Here's the galaxy seen as a negative, and here's what's seen in, so it's in the near ultraviolet, oxygen 2, so it's ionized gas, and it produces this huge, huge halo of gas, which is, again, 100 kiloparsecs, so that's 300,000 light years in extent. And compare that with what's going on in M82. So there are some real barn burners out there which are really having their way with their surroundings. Okay. What else can they do? They can do the same thing which was done with the Fermi bubble, but they could do it with distant galaxies which happen to have quasars behind them, or even bright galaxies behind them. They can use those objects as searchlights to probe the intervening material. And that can be done with the next generation of wicked large telescopes. So that's what we have to look forward to, is that sort of probing of the galactic winds from more distant galaxies. So that's it. Galaxy blowhards, or how I learned to love galactic theatrics. I hope you enjoyed this, and I look forward to any questions that you may have. And I'm going to stop sharing the screen. And
there you go. Thank you, Bill.
there you go. Yeah.
Thanks, Bill.
Yeah. Does anybody have any questions for Bill? Bill, I thought those lines coming out of the core of the Milky Way that were probably not cometary tails. Didn't they look like solar phenomena, like magnetic lines?
Oh, I'm so glad you said that. They remind me of spicules.
Yeah.
Yeah. And those are highly magnetic objects. They're the results of magnetic reconnections, magnetic field reconnections on the magnetic carpet of the sun, the so-called magnetic carpet. And so I'm glad you noted that, because that's what they reminded me of. But, you know, that's just an aesthetic resemblance.
And they reminded me of contrails.
Contrails. That's interesting too. But the fact that there, some of them, at least a few of them, are emitting in the X-rays makes me wonder whether they're actual contrails, or it would suggest higher, more energies to make that gas hot enough to emit in X-rays.
Mikas, you don't look happy to be wearing a mask.
I don't see him.
What's good about COVID?
Oh, there you are. Yes. It's the new emoji.
Does anybody have a sacrificial pie or a Twinkie or something they'd like to eat before we say goodnight?
I guess I'd like to say that if I ever do any more research, this would be the area, these starbursts. Maybe not on the distant galaxies, but on stuff closer in. I think the balance of what's actually making them shine and glow, and what structures them, I think those questions have yet to be answered. And so that would be kind of a fun.
We have a question in the chat window from Brewster, who doesn't have any audio. He says,
He's muted.
Well, he can unmute himself. He
Is
says no
S
audio.
star considered to be not moving relative to the rest of the galaxy? S star, you mean Sagittarius A star?
That's got to be what he means, yeah.
It is the center. So that's the pivot. And that pivot, with respect to the rest of the galaxy, that's what stays put. But actually, that's a very good question. What if it was like wobbling a little bit?
How do you know it isn't?
I don't know whether it is or isn't. You'd have to get a spectral line from that
Move, yeah.
object and then track it.
Yeah. I have a question. All the globular clusters that we know in our Milky Way, there's maybe 150 to 200 of them.
Yeah.
Were they all at one time centers of a galaxy that fell apart and left all the star formation, or what? They were very old, of course.
I wish I could answer that question. I favor that answer, that they were the cores of galaxies that got gobbled by the Milky Way galaxy. There is some evidence in that direction, but
Well, the question is, they're galaxies within a galaxy, essentially, if that was the case. So are there other galaxies within the Milky Way that are going to do this or can do this? Or are all these other galaxies we look at actually outside of the Milky Way?
Of course they are, John.
They're all far enough away, yeah. I mean,
yeah. But we do have the Sagittarius dwarf galaxy, which is getting eaten by the Milky Way right now.
and then the Milky Way is going to eat up the Andromeda one of these days too, or
Well, that'll be a fight to watch.
who wins? Yeah,
that would be one where you'd want to buy tickets, because they're equally matched. But I wish I could tell you an answer about the globular clusters. It's possible that they were made another way, though I find it difficult to.
Well, there's no nebulosity around them. I mean,
Right.
no garbage and dust and everything else, and
Right.
they're stars that got formed somehow, and they
I
think
know.
it's done by compression probably, or shock waves or something. But if they were part of a galaxy, you'd think there'd be a lot of other crap around.
Yeah, and the big ellipticals, they got what, 1 million globulars?
Yeah.
Right.
That's a lot of galaxies to eat. I don't know.
Yeah.
So
Anyway.
I have a query here by Ann Zeiser. Hello, Ann. I'm on for my 16-year-old who's not on because he's celebrating his birthday today. Do you ever need assistance for your research, or would you ever consider being a guest at the Linfield Science Club? Ann Zeiser from Matt Neutralia. That was privately, but I just noticed.
You're a lucky man.
Yeah, but I think that is something that we might all consider, Linfield Science Club. So I will contact. Well, Anne must be on the email list, Mike.
Yes, if she's here.
Can you hear me?
Yes,
Yes,
sure
we
can.
Well, yeah, I'm brand new, so I actually got into this because of Phil Orbain,
Yes.
so who was an old associate and friend. So, yeah, we can figure it out as long as somebody has my email. This is my first time ever joining this.
Okay, and I'm going to leave that to Michael to close the loop, okay?
Yeah,
Okay.
great.
And
Wait, though, stick around for a minute, okay, Ann?
Sure.
All right.
okay. We like closing loops.
Sounds
All
good.
right. You guys want to, we don't usually meet in August, but the rationale for that kind of pales with the COVID stuff, since everybody's going to be sitting on the same couches at this time next month as they are now. Do you guys want to meet next month, or do you want to take the month off? Let's see. Hang on a second. I wish I had more experience with polling. I'll tell you what. Turn your camera off if you want to take a month away from GAAC and start again in September. Turn your cameras off. It's in the lower left-hand corner of your screen. Leave them on if you want to have a meeting. We'll give you a minute. I only see a couple of no votes. Okay, well, Steve, you find us somebody. All right. Good seeing everybody. I'm glad you all came. Bill, good job. That was really fascinating. I don't think I'll look at M82 quite the same way.